Hey, welcome to the introduction to limits. Limits are a big topic in honors calc and calculus in general. So this is our first lesson on it. Limits are a way to describe what happens to y values on a graph. And we know these holes, breaks, or patterns to be discontinuities. That's where we have the most trouble describing what's happening on the graph. So we'll see a lot of piecewise functions in these examples. And algebra does a little bit of what we know about polynomials, what we know about increasing and decreasing functions is important, but limits are another way to describe what happens, especially when we have strange features like asymptotes. And our definition of a single-sided limit is the value of y, f of x, so the outputs, as they approach a given x value. This word approaches is going to be used a lot. So we'll think a lot about these limits with movement towards a given x value or approaching that x value. And there's some symbols we use for limits. So the limit as x approaches a from the right side, to the right side of a, and then the limit as x approaches a from the left side is just indicated with a negative as the superscript or the exponent on a. So if we're approaching a from the left, we'll be starting from the left and going right. And we're approaching a from the right, we'll be starting from the right and going left. So that can be a little bit tricky when you are looking at a graph, making sure you're keeping everything straight. And over here, a limit at a value, so this is a little bit different than just the right side or left side limit, how to describe what's happening on the right or left side of a value. A limit at a value exists, so there's a new word there, exists, if the left and right side of that value are equal. So if the y values are equal at that point. So we'll see some examples of that. Existing for a limit is kind of what we use to just describe it in general, like is there a limit there to even talk about? So if there's not a limit there, then there's no limit to talk about. For this example, we are determining the following one-sided limits based on this piecewise monstrosity. And for a, if the limit as x approaches a, so the a on the graph here, the right side of a, what's happening on the right side of a? Well, if we approach a from the right, then we follow the curve, and what y value is that graph approaching? Well, it's up against a vertical asymptote, so it's approaching infinity. For b, the limit as x approaches a from the left, this side is approaching negative infinity. So we can use infinity as answers here. For c, what's happening on the right side of b? The right side of b is over here. We can start from this piece and work our way left to find the right side of b. The y value, what that looks like it's 1.5 just about. On the left side of b, looks like it's hitting at the y value 1. Follow this graph towards the left side of b, and you should get 1. So a quick note, is there a limit at a? If I'm going to add a little sub-question in here, this is asking for what's the limit at a for the function. We've already checked the left and right sides. Are the left and right sides, are the y values equal? No, they are not. So based on this definition, the limit does not exist because the left and right sides of that value a on our graph are not equal. So in order to indicate that, we would say D in E does not exist. Does the limit of b exist? On our function? And you would also put no, D and E. Their y values on the left and right are not equal. And just to check on whether you're reading this graph appropriately, what is the function value at 0? That would be 1. That equals 1. And we'll go and look at C. What's happening at C? C has a clear break, so a discontinuity, a jump between the y values. So the left side of C looks like it's 2.5. The right side of C is, I don't know, about 0.1. For this example, the axes aren't very well marked, and it's not very clear on the graph what you're looking at. Like, I think we could get away with 2.3 here, but just for the sake of example, this graph is pretty good at describing the left and right sides, just because it has those breaks in it. And lastly, I here for this example, what's happening on the right side of 0? The right side of 0 is this graph. So this point up here does not matter. It is not a part of the right side, because remember, we're using this language approaches. So what's happening as we approach x equals 0? X equals 0 is right here, so that translates to this y value. So we would respond to this question with the y value, negative 2.5. Alright, so there's some examples. Now, we're going to talk a little bit more about, we're going to make sure we have this logic down about proving a limit exists. You have to show that the right hand and left hand limits are equal. So for the left side of, or the right side of negative 2, which is right here, that limit is 1. We're approaching the y value 1. We're approaching the y value of 1 for the left side of negative 2. Here's the left side, we're going to 1. Here's the right side, we're going to 1. So that means that the limit at negative 2 is 1. It's pretty sound logic once you have indicated what the left and right side limits are. It's pretty easy after that point. For f of negative 2, what is the y value? So what's happening when the y value, or sorry, when x is negative 2, what's the y value associated with that? Well, we see an open circle, so we're not forgetting what we learned about piecewise functions and just domain and range in general. This is undefined because there's no y value associated with x equals negative 2. Now, we're asked a little bit more of a a little bit of a tricky question. It's not asking us just straight out what are the limits at certain, like at specific left or right sides, but we need to show that the limit exists at a value. So we have to show that the limit as x approaches 3 from the left of our function is something. And then we have to show that the limit as x approaches 3 from the right on our function is equal to something. And if those two things are equal, then we can say that the limit as x approaches 3 on our function is equal to something. So let's go look. What's happening at the left side and right side of 3? Ooh, so this is on a curve. We find the y value, and it definitely looks like we have a left and right side limit that equal each other. So this is on a piece of the function that is not discontinuous. We'll talk more about what continuity and discontinuity mean, but we know that there's no breaks, there's no holes, there's nothing like that. So we're going to call that about 2.7. So that means the limit exists at 2.7. So because the left and right sides, if you're writing this out, because the left and right sides are equal, then the limit exists as we approach 3. X equals 3. Alright, does the limit exist at x equals 1? Give a reason for your answer. So mathematically you could do what I wrote down in A as your answer. And that would be a really good explanation. So does the limit exist at x equals 1? Alright. Automatically we can tell that there's a break in our y values. There's a jump. So as we approach 1 from the left and 1 from the right, we go to 2 different y values. And however you want to describe that, you can say that in words. I'm going to say the limit as x approaches 1 from the left on our function is equal to -3, and the limit as x approaches 1 from the right of f of x is equal to 1. -3 does not equal 1, of course, so the limit doesn't exist. And that would be it. As long as we described what happens with the limit using the limit definition on the left and right sides, then you're good. You have to have the left and right side information in your explanation. There's not really another good way to describe what's happening. So there you have it. That's your first lesson on limits. Make sure you're following along with the practice and that you can see that easily in Google Classroom. Thanks.